Everyone, this is Dr. Dadu here to present first discrete time modeling and Python. Happy listening. This is the first of my two videos on discrete time models. In this presentation, Python codes are used to analyze the popular pre-predator system. In the second video, it will be another system, but this time around it's pre-predator. As usual, I've assumed that my audience are aware of the theory concerning the presented system, and that my task is to provide as easy as possible a set of Python reusable codes that will automate the statistical modeling. Now, the materials that will enable us to be on the same page are the installation of Anaconda, and within it is the Python 3, Matplotlib, MumpyLib, Pandas, etc. All the installations are to provide you with the opportunity to run Jupyter Notebook. All right. Some basic knowledge of coding in Python 3 is essential. However, ability to code in Python 2 may be sufficient if and only if you can install and use a conversion program known as 2 to 3. Now, note, Jupyter Notebook is the utilized interface. The presented discrete time modeling technique will enable the researcher to easily obtain the trajectories involved in his or her models, thus creating room for visualizing stability zones and further analysis. The model for the popular Lotka-Volterra equations in its discrete time presentations form will be used for illustration in the Python 3 environment in this video. Right. Discrete time modeling and Python. Now, the derivation of Lotka-Volterra equations for a simple predator, that is XY system, X for prey, Y for predator, use the following discrete time equivalent, equations 1 and 2. All right, where R is growth rate, D death rate, B determines how quickly the death rate of predator increases as Y increases. C determines how quickly the growth rate of the predator increases as X increases. CAPAC, the carrying capacity of the resources of the environment. How much animals can the environment provide for? CAPAC. See, if the resources are plentiful, then it can carry as much animals as possible, be it the prey, be it the predator. But if the CAPAC, if the resources are not too plentiful, are not much, then the lower the number of animals can sustain. Now, to continue, if we put these constants inside the equations 1 and 2, it will become equations 3 and 4. Now, if we supply these two equations to Python in the Jupyter Notebook environment, we will get nice results, which we will see later. These are the codes, but obviously in the Jupyter Notebook environment, it's more colorful than this. It's just that I cannot afford it. There ought to be space here, space there, space somewhere here, and space here. Now, if you provide this Jupyter Notebook, you're going to get this as an output, as well as this. This first one is talking about the relationship existing between the predator and the prey. If the food is plentiful, the number of predator will increase because the atmosphere will be conducive. It will multiply. When food drops, the population of the predator also drops because there won't be much food in the environment. Okay, this is the trough pit web. It is said to be egg-shaped. Visualization shows in slides 6 and 7 often assist the modeler in the analysis phase of the respective models because the audience are usually more satisfied with pictorial representation. In slide 6, it was shown that irrespective of the number of cases or scenarios, the trajectory do not change beyond shrinking. You will see that later when I try to mount the Jupyter notebook. They shrink or magnify. The codes are in OOP format, object-oriented programming format, and hence reusable. For instance, if the modeler wants to visualize the effect of a perturbation on the system, he or she will merely rewrite the code to reflect the presence of the perturbation and supply the refined model and the codes to the Jupyter notebook and run. The truth of the matter, the perturbation, let me think of one. Inbreeding depression. Inbreeding depression is a perturbation. And researchers have shown that it affects the predator more than it does the prey. Fine. Somebody can say, predators are usually larger in size compared with their prey. But there are some prey that are also larger. For instance, a buffalo and a lion. Buffaloes could be bigger than a lion. A giraffe and a lion. The giraffe may be bigger than a lion, yet the giraffe is the prey, the lion is the predator. So, but inbreeding depression affects the predator more than it does the prey. So, if you introduce a perturbation like that into the system, the trophic that was egg-shaped will become elliptical. All right. Let me try to show you what the notebook looks like. Yes. Let me take it from the beginning. Like I said, it's more colorful. You see, the imported libraries, initialization, then this is the system, Lord Cavutera Predator with the constant supply will look like this. And this is the first case to show what will happen if there are few animals in there. When there are more animals, like I said, the shape does not change, it only shrinks or magnifies. And finally, the trophic web. Now, this is the farthest I intend to go with first discrete time models and Python. Watch out for my videos on the next in this series. Please like, share, and subscribe. Thanks for listening and bye for now. Thank you.